Part 2 of How to Improve Your Bioengineering Projects, Lessons Learned from the City of Calgary Repair and Monitoring Program, is about project planning. In this presentation, we'll be covering project goals and objectives, site assessments, team expertise, project scheduling, materials procurement, bioengineering techniques overview, performance targets, and project documentation. Bioengineering project planning starts with having a good understanding of the project goals and objectives. You might ask yourself, what is this project attempting to achieve? Is it stabilizing erosion in a creek or on a slope? Is it for habitat or riparian health enhancement? Or is it aesthetics? Or is it mandated by a regulator? Or it could be a combination of all of these. Defining clear project objectives at the outset allows for the development of appropriate solutions and allows to evaluate the success of the project at its completion. Some common goals include erosion protection or site stabilization, bank or riparian restoration, flood safety, or societal goals. Actually visiting the site is probably one of the most important parts of the planning process. On site, you can better understand the conditions and processes occurring at that site to then identify an appropriate solution that will properly address the erosion problem. There's nothing worse than spending a bunch of money to fix a problem to have the problem pop back up because of an unanticipated issue that could have been identified during a site visit. So things that we'd want to document during site assessment include confirming and verifying the project goals. For example, if the goal is to stabilize an eroding bank, it is important to verify that a bioengineering approach will work, or that it is needed based on how the natural system is responding to the disturbance. We'd want to document flow patterns in the stream or overland. The presence of any seeps or groundwater features are useful to note. We'd want to take a look at undisturbed areas to identify reference or control sites and observe how they are functioning to support a design. We document erosion features such as bank erosion, surface rilling or gullies, and slope instability and their potential causes. We'd note existing vegetation species and their distribution at the site, also noting the vegetation trim line for riverbank erosion stabilization projects. We'd also note invasive species that may be a concern in the future. We document aspect to observe how warm the site might be and shading from buildings or existing vegetation. We'd also want to observe for soil conditions that might affect vegetation establishment. In particular, we'd look for evidence of soil compaction, such as this old logging road, or anaerobic soils, saturation, clays, toxic conditions, etc. We'd note human and wildlife activity, so we're looking for trails, either formal and or informal, and trampling and browsing. And for construction planning, we consider available space to construct and access to the site for equipment, but also for any observable overhead or buried utilities or fences and gates. Planning the team for the site assessment and for overall project delivery should start with the understanding that bioengineering projects draw on the experience and knowledge of several disciplines. This bubble diagram shows an example of the interdisciplinary team that was needed to deliver a large bioengineering project in Calgary. The expertise and disciplines included design and engineering shown in blue, environmental shown in green, and stakeholder and rights holder engagement and education in purple. While this may not be needed for all projects, particularly smaller, less complicated projects, it is still important to know what types of experience might be necessary for a successful project. Planning project scheduling often leads to identifying critical path tasks that affect the overall project delivery schedule. Obtaining regulatory approvals for proposed works often falls on the critical path, since they can take anywhere from 2 months to years to obtain, and if a project needs to be constructed during a specific period, they should be planned for well in advance. With respect to the regulatory approvals process, bioengineering offers several advantages over conventional approaches such as riprap, as shown in this figure. Bioengineering has lower risk to fish and fish habitat, lower complexity of fish habitat assessment needed to support a regulatory application, shorter duration of project review, and lower amount of offset required by DFO. Additionally, some jurisdictions, such as the City of Calgary, require bioengineering approaches or justification as to why they have not been used. Other often critical project considerations that affect the overall project delivery schedule are environmental windows and site conditions like winter ice. When these windows are assessed when planning construction activities, as you can see here in this chart, they can overlap and not leave any room for construction. And then add in the high public use period, then the situation looks impossible for scheduling construction. There are a few ways to navigate this, and I'll use an example of one of the Repair and Monitoring Program sites to describe one way. For this project, tree clearing was completed outside of the nesting window as a separate activity to the overall construction sequence to reduce the chance of nesting during the main construction period. Then, the project team negotiated with the regulators to have additional construction time within the fisheries restricted activity period, but subject to additional mitigation measures. Then, construction could proceed during extended spring and summer windows, but the site wasn't ready for planting in the spring, and as you can see, planting is not recommended for summer for conventional planting materials. So the team worked with the contractor to procure a hybrid live stakes container plant product referred to as tall-rooted stakes for use during the summer months. These strategies allowed construction to proceed in July, August, and September, but advanced planning and scheduling was needed for this to work. So this analysis of available construction windows is an important part of the planning process. On the last point about vegetation installation timing, you might ask yourself if planting in summer is such a bad thing, especially given the pressures for getting construction complete during low water conditions or during fish windows. If there's anything to take away from this workshop today, it's that installing live cuttings during recommended periods will increase the chance of success for a bioengineering project. To illustrate this, the part of the photo on the left shows a section of timber crib wall where live cuttings were installed outside of the recommended period in August, and the part of the photo on the right shows the live cuttings that were installed within the recommended period in April, when live cuttings were dormant. There are hardly any live cuttings still alive on the left, but on the right, the vegetation is establishing nicely. We ended up developing a recommended planting schedule for native plant seeding, container plants, and live cuttings harvest and installation, as shown in this table that's provided in the final program report. Planning for the type of materials to be potentially used in construction is important, since procurement of some vegetation types and species can be months or years, because it takes time to grow plants. For example, the supplier might need to collect the seed in fall and grow the plant over several months or a year to get the species and size of plant that you want. Last-minute plant orders can often result in substitutions for species or stock type that may not always meet the design intent, if there are any plants left, which can be a problem when looking for popular native plant species at the last minute. Similar to the living materials, having a rough understanding of what structural materials might be used in construction at the planning stage can be important, since procurement lead times or supply of material might impact the design. For example, large rock is not locally available and too expensive to import in many areas, so a different approach will be necessary. To further the planning for materials procurement, regulatory approvals, and construction methods, now that there is some level of understanding of the site, some initial thinking about design can start. So what techniques might be suitable for the site given what we know now? The purpose of this exercise at this point in the project is to start thinking about what bioengineering techniques can be used to address the erosion or stability issue observed at the site. A useful classification of bioengineering techniques for this purpose is plant-based or soil bioengineering approaches, as shown in the top of the slide, and living structures or biotechnical approaches, as shown at the bottom of the slide. This is useful to think about because for the plant-based technique, there are no or limited structural materials included in these techniques, so the vegetation, often supported by biodegradable matting, is being relied upon for erosion protection. In most cases, these techniques can be constructed by hand without the need for heavy equipment. Projects that are built by volunteers are often based on these techniques. The examples shown here are branch packing, brush layers, brush mattresses, fascines, live pole drains, live staking, and wattle fencing. For the living structures, a combination of living and structural materials are used to address erosion issues. In most cases, these techniques require more analysis and design and require heavy equipment to construct, so have a larger disturbance footprint than the plant-based techniques. But they're usually the type of approach selected to stabilize eroding riverbanks to protect critical infrastructure, for example. So the examples shown here are live slope grading, vegetative retaining wall, vegetative riprap, vegetated soil wraps, and vegetated timber crib walls. We will look a bit more in depth at several of these techniques in the next presentation, but having an idea of what techniques might be used will help to plan for the level of effort for design, construction, and associated regulatory approvals. More information about each of the techniques shown in the last slide can be found in many of the books and manuals shown here. These references and others should be consulted during project planning and design for additional information and best practices. In a similar manner to project objectives, consideration during the planning process should be made for how to measure performance of a site once it's complete. There are surprisingly few performance targets in the literature, so we took the targets from Schechtel and Stern's Water Bioengineering Techniques book from 1997, as shown in the table here, and compared with establishment results from our Calgary Repair and Monitoring Program data, and found the targets were achievable for bioengineering projects in Calgary. We ended up recommending using survival, cover, and density targets like the ones shown, with survival measured for year 1 post-construction, then woody cover and or density from year 2 post-construction onward for a minimum 3 but up to 5 years. This allows the performance to be measured initially on material installation quality, then transitioning to what the end product that we are looking for is, 100% woody cover to maximize the erosion protection from woody plants. Project documentation should be considered as part of the planning process, since funders, regulators, and the public might all have interest in a detailed understanding of the analysis, design, and construction of the project. The chart here shows a list of possible project documentation that was compiled as part of the Repair and Monitoring Program. We found a trend in the Repair and Monitoring Program results that pre-construction documentation related to the start of the project, such as design reports, drawings, and technical specifications, were most often produced and available, but availability of documentation waned for construction or post-construction, where maintenance records and construction completion documentation like record drawings or as-built reports was available for less than 40% of the sites. While individual projects will have different documentation needs, but overall, properly documenting what has actually occurred in a bioengineering project is important, and so creating a list of what documents will be needed at the start of the project will help with setting expectations, scheduling, and budget, and will help to make sure that proper documentation is completed at the end of the project so that funders, regulators, and the public understand what was done. So in summary, define project goals, objectives, and performance targets at the start of the project. Develop a multidisciplinary understanding of your site. Schedule design activities to meet available construction windows. Plan for materials procurement so that the right materials are available for the selected bioengineering approach, and document your project. Now it's some time for questions and discussion.